You turn the steering wheel and the car turns. Simple, isn't it? But at higher speeds, the car doesn't actually follow the steering angle. You have felt it. Parking feels easy. Normal turns feel natural. High speed turns, however, feel unpredictable. What really makes a car turn? And why does it behave so differently at different speeds? In this video, we will break down the real physics of turning, slip angles, tire forces, and the role of steering geometry. Hello, I am Aravind. Let's continue the question we asked. What makes a car follow a curve? An object in motion wants to keep moving straight. If no force acts on it, it will pass the curve and keep going. To make it follow the curve, you must apply a force toward the center of the curve. That inward pull keeps the object on the curved path. If that inward force stays constant, the object moves in a circle. For a certain mass, the acceleration required to stay on a curve depends on speed and radius. Mathematically, acceleration equals speed squared divided by radius. Let's imagine you are driving through a curve. Inside the car, you feel pushed outward. That's not a real outward force. It's your body's inertia resisting the inward acceleration. From outside the car, it wants to continue straight tangentially. The centripetal force generated by the tire is what changes that direction. So in a car, how the tires generate centripetal force? Most people say friction. Friction is the effect, but what's the real cause? Let's find out. When you turn the steering wheel, the tire changes direction, but the rubber at the contact patch doesn't instantly follow. The contact patch rubber is gripping the road, so it resists the change in direction. What happens because of this resistance? Let's find out. Observe a small portion of the tire represented by the blue segment. As the tire rolls, this segment enters and leaves the contact patch. Consider the vehicle is taking a left turn. The tire segment follows the steer direction at first. But once it enters the contact patch, it can't maintain that direction. It gets pushed sideways, deflecting laterally. The deflection increases up to a point, then decreases as the segment leaves the patch. This shear deformation makes the tire push sideways against the ground. Static friction opposes this push, creating an equal and opposite reaction, the lateral force. The pressure builds as the segment moves through the patch, peaks just after the center line, then decreases. The combined lateral force from the entire contact patch becomes the centripetal force that turns the car. Interesting, isn't it? The contact patch's resistance to wheel's direction change creates the lateral force. How do we define it so that we study lateral force better? Here comes the slip angle. Slip angle is the difference between the tire's heading direction and its actual direction of travel. Let's look at now how the lateral force changes with slip angle. The slip angle versus lateral force curve has three regions. First, a linear region where lateral force increases proportionally with slip angle. Between about 3 to 8 degrees, the force still increases but no longer linearly. Then comes the saturation region where the tire reaches its maximum lateral force limited by static friction. Slip angle is a real mechanism behind how a car turns. It's the tire's resistance to wheels direction change. This resistance creates a necessary lateral force which is required to keep the car on the curve. In the next video, we will look at how slip angles behaves at low speeds and why steering geometries like Ackermann becomes important. Thanks everyone for watching.